Resonance can seem very abstract, so let's see a real application of how resonance affects acidity. Let's draw two molecules. One is going to be ethanol. And of course, what are we going to do with ethanol? We're going to react it with a base. In this case, it's a very weak base, water with a lone pair. That lone pair will attack that hydrogen, break this OH bond, and set up an acid-base equilibrium. And I'm going to complete that. Let's put them over here. We've got two lone pairs over here already. So there's one acid-base reaction, that's with ethanol. We can also have a very similar structure. This is acetic acid. I'm going to try to draw this a little bit more compressed. Let's see if it works. If we have water deprotonating this structure, the lone pair on oxygen attacks that hydrogen. The OH bonding pair gets deposited onto the oxygen, the other oxygen. I'm going to draw our water over here, our hydronium over here. So, as it turns out, these two acid-base reactions, you might initially think they should be very similar because both of them form O- anions, and you say, well, the electronegativity is the same, the size is the same, therefore the pKa should be the same. Well, the pKa's are not the same. pKa of ethanol is about 16. The pKa of a carboxylic acid is about 5. That's a big difference. That's 10 to the 11th times more acidic. It's a big difference in reactivity. So this can't simply be an argument about electronegativity or size. It's something else. And of course, what is that something else? It is resonance. As you can see, resonance is a very powerful effect, as in, 10 to the 11th times more reactive. So what's happening here is somehow this anion is able to delocalize this O- by means of resonance. So what we have is a situation that looks exactly like the most common application that we thought we'd see resonance. We have two atoms attached by a double bond, and then another atom with a lone pair next door. What do we do with this? We said, oh yeah, that lone pair dumps down, makes a new BC double bond, and that breaks that bond. So that's exactly what we're going to do here. We're going to take one of these lone pairs, make a new CO pi bond, and the other CO pi bond is going to break. And now we can draw a new resonance form. We use our double-headed arrow to show resonance forms. And our mechanism leads us to draw this structure. And you might say, Dr. Stevens, that is the same thing. Let's not forget our charge. It is the same thing, but the fact is there are two oxygens here, this lower oxygen and this upper oxygen, and they are now able, through resonance, through delocalization, through the p orbitals of this molecule, they are both able to share in that negative charge. That negative charge is not localized on just one oxygen. It is now spread out or delocalized across two oxygens. And that makes this anion more stable than having the localized anion. More stable how? Well, it's more stable, it is less basic. And because this anion is less basic, therefore the parent acid is more acidic. And how do we see that? Well, we see that in the pKa's. It's this acid, this lower acid has a pK of 5, upper acid ethanol, which is not, you cannot delocalize this negative charge. The pK is 16. The big difference in acidity. So here's a specific example of how resonance increases the acidity of an acid.